geometrical optics. Okay. Also known as ray optics. So what essentially we are going to learn in this chapter is about mirrors and lenses. And here a concept of a ray is introduced. So what we mean by ray and what ray signifies? So we all know that light is an electromagnetic wave. So when I say light as a ray, then we only talk about the direction of propagation of energy which is carried by the light. We do not see the actual oscillation of electric or magnetic field. So in the concept of ray, we consider direction of a ray as direction of propagation of energy. Carried by light. Also, what we consider here is the only part of a spectrum which is called the visible region, because in the geometrical optics all the image formation can be viewed only if it is falling within the visible spectrum of light. Other spectrum of light like UV and infra, we don't see or perceive, so we don't consider. So ray is a concept and it only denotes the direction of propagation. So we do not consider the oscillation part, although we have a wave like this, maybe. But in ray optics, we only consider a line which is kind of signifying the direction of propagation of energy. So energy is the important concept that we consider here. Now, you will study later on in the chapter of electromagnetic wave that direction of propagation of energy is given by direction of propagation of energy is given by Pointing vector. So this pointing vector is very famous in electromagnetism. So the S vector we write as 1 upon mu naught where mu naught is the permeability of free space. And why this formula is important for you? Let's say we have an electromagnetic wave in which the direction of oscillation of electric field is along the y-axis, and the direction of oscillation of B is along the z-axis, then in which direction the energy will propagate?
X-axis.
Very well. So the E is oscillating this way. And if B is oscillating this way, in two different planes, then the direction of propagation of energy will be E cross B, which is x-axis. So this is called the direction of C. All right. Okay. They may give you just E and B, and they may ask you that how it is going to propagate. You may realize that these are oscillating fields. Like this. So electric field is oscillating, and so the magnetic field in different plane. Okay. So now the light ray, although these electric fields are and magnetic fields are oscillating this fashion, but the light ray we assume propagating in one direction. So the concept of ray optics is applicable when the light intercepts those objects which are much bigger in size compared to the wavelength of light. So for example, if the light ray is hitting the sub-elementary particle, let's say electron or something else, the entire consideration of a wave, the ray is will be wrong, because the object which the light is facing is not having large size compared to the wavelength of light. So the application of ray optics you may call it application domain. In the ray optics, generally light which is a wave And every wave will have some wave-like properties, some characteristics like diffraction. So those phenomena are so insignificant that we can consider the ray approximation. So when the light is intercepted by various optical medium, then it does not undergo any significant change in the, you can say, the blurring part, or maybe the diffraction part. Okay, anyway, I will discuss those things actually in detail later on. So you can just remember that our test domain is not everywhere. So there is a very specified distance which under which we can apply it, and that's called the Fresnel distance, which I will teach you in the wave optics. So it is applicable within it is applicable within Fresnel's distance. And for length, the Fresnel distance is defined as roughly so A square by lambda. Well, A is called the aperture. So we'll come back to the aperture again. So well, let's talk something more about the light. So what is light? It is an electromagnetic wave. It is made of massless particles called photons. It carries energy as well as momentum. So this is the some of the property of the light. So it's an electromagnetic wave. It is made of massless particles called photon. It carries energy as well momentum. So basically, in situation, we can also treat light as a particle. Particle means the wave is like a confined object. So we do have a wave, but the wave is kind of confined between a very, very small, tiny space. So such a spread of wave in a localized fashion is called particle. So you can say localized form of energy. We call it particle. So when I say light as a particle, then we mean the localized form of energy. And when I say the a wave, then it means the delocalized form of energy. It means it is everywhere, it cannot confined. So if you want to differentiate between the wave and a particle, the wave is the delocalized form of energy. So the beginning and the end is not confined. You can't decide the beginning and the end. I mean, it is spread everywhere. So that's the concept of wave and particle in physics. So in this chapter, we will start with something called object and image concept, because that is what we are going to learn about in this chapter. So for every object, we have some image, and for every image, we have some object, and we need to understand these two concepts strongly. So concept of object and image. Okay. So object and image. First of all, we need to understand that object means the physical object. So for any optical element, now what is the meaning of optical element? These the mirrors and lenses and prisms all are called optical element. So let's define something called optical element. We can just remember that mirrors, lenses, prism, slab, glass slab. So in fact, what I can say that anything which is capable of bending light is called optical element. So anything which is capable of bending light, we call optical element. So the object and image concept is a relative concept, not the absolute concept. So we'll see through an example and we'll try to understand the concept of object and image. Okay. So first I'll give you the example and then later on I will try to explain what exactly happens. So let's say we start with something, maybe a flame of a candle. So imagine the dot above the flame as the object. I'm just trying to replace the body with a point. A body is called extended object, and this is called point object. What we need to understand that an extended object can be thought as a combination of infinite point objects. Give me 2 minutes.
So can you repeat that, please?
Pardon?
Can you repeat that?
Yeah, what I'm saying is that every body can be thought as combination of infinite point object. So when we have the extended object, we can replace that by infinite point object, right?
Yes.
Oh, give me like 5 minutes break, I'll come back. So were you not aware of the lecture timing?
Sir, sir, I didn't saw the lecture because my phone was switched off. Yesterday, sir told that it will be in afternoon, so I thought we will start from 12.
Okay. So let's start. So what we are going to discuss is the concept of object image. Concepts are very vague in nature, so sometimes you may get confused about the object and image. Object has nothing to do with the real physical object. When I say object, then of course the idea is not the physical object. The idea is something more than that. So of course the light ray, we need light ray actually to define both of them. So whether you want to define the object or if you want to define the image, in both cases we need light ray. So let's say we have a physical source, something real. If something is real, then light ray will emerge out of it in all directions. And of course, the light ray will go in the other direction also. So there are infinite light rays coming out of this point object in all possible directions.
So these rays are emerging from the peak of the flame.
Yes, the light ray is coming out of this flame. Now these light rays are called incident rays for the lens, right? What do you call?
Incidental.
These all are called incident rays. Now, when the light ray will incident on a surface, then two things will happen. It may pass through it or it may reflect back. So we say that either it will refract going to the other side, or it may reflect back coming back to the same side. And that depends on the optical element chosen. So if you choose the mirrors, then the light ray has to come back. If you choose like prism or lens or glass slab, it will suffer a refraction and will go on the other side. Okay. So now the incident ray for the lens will tell you the location of object, or in a way you can say that object is something which is decided or defined by the incident rays. So how to get the object for the given instrument or the element actually? The way is simple. The lens which you are looking at right now, these are the incident rays. So what you do is you trace back the ray. If you trace back these rays, take any two, at least two. You can see the two. If you trace any two rays, it will meet at a point, and the point is called the point of emergence of light. You can think like this. But for the lens, the point of convergence, you can think this way, is called the object for the lens. So object is defined by the incident ray, and what we say that this is the object for lens. So how we get the object? The answer is by tracing back the incident ray. Understood?
Yes.
Now imagine scenario. We'll come to that later on. So you're tracing back the incident ray, and if you're able to get the point of intersection, then you can say that the light ray is coming from here. So such object which can actually be obtained by retracing the incident rays, which is called real object. So real means the light ray is really intersecting, actually intersecting. So imagine that after the refraction, the light ray is going this way. I'll just take two. But in the path, you bring a mirror. So you have brought a mirror in this path.
So,
Yeah.
so can we repeat the real object definition again?
If the incident ray you trace back and if they actually intersect, we call it real.
Okay.
So for the lens, if you trace back the incident ray, are they intersecting?
Yes.
All right. Now imagine these two light rays which is hitting the mirror. So now these two light rays are called the incident ray for the mirror. Okay. Now try to trace back. If you try to trace back these two light rays, they will never meet. In fact, it will diverge out, isn't it?
Yes.
What does it mean? You cannot trace back actually. So when you fail to trace back actually, what you do is you extend the line in the other direction. Now this is, we denote by the dotted line. Why? Because we know that the light ray is not able to reach there. This is the extension of the incident light. See, we have to make the light ray meet either by tracing back, but if it fails to trace back, we extend it forward and we meet them virtually. So we let them meet virtually, and therefore this point is called object for mirror. But which kind of object?
Virtual.
Virtual. Because of the obvious reason, the incident ray is actually coming there, or it is virtually coming there.
Virtual.
Virtual.
That's a very common sense. Okay, what is called virtual object? Okay. So what we need to realize that it is the incident ray which decides the object position, and it is different for different optical element or instrument. So here mirror and lenses are the optical element, and you can see that they face different light ray as incident rays, and therefore there is no absolute definition of object. You can see the object of the mirror is on the right side, whereas the object of the lens is on the left side. Is this clear?
Yes.
Okay. Now we'll come to the next part, the refraction or the reflection. The light ray, after passing through the lens, has refracted, correct? You can see.
Yes.
Now, when we talk about the reflected or the refracted rays, we talk about the image. We can say that image is obtained or defined with respect to the reflected or refracted rays. Okay, so reflected or the refracted will decide the image position. So for the lens, if you trace in this direction, we only look for the direction at the exit point. We don't see further. If you trace this direction, will they meet actually? Yes. If you trace, they will actually meet, yes or no?
Yes, sir.
And
Sir,
therefore, yes.
sir, I didn't understand the question. Can you repeat the question?
For the lens, the refracted ray, now you have to trace, because the image is defined in terms of a reflected light or a refracted light. Just like object we define for the incident light, the image we define for which light?
Refracted.
Refracted or
Reflected.
reflected. So for the lens, if you follow the refracted light, will it going to meet somewhere?
Yes.
So this is the actual meeting. If you trace,
Yes.
this is called the image of lens. And which image? The real image. Understood? So this image is the actual or real image of object made by the lens. It is clear? And what we
Yes.
can also realize that the image of the lens is basically the object of the virtual. It is a virtual object of the mirror. Okay. Now, after hitting the mirror surface, the light ray will reflect again. And because it will reflect, you can get a point of intersection again. So for mirror, these two light rays are the reflected one, correct?
Yes.
So the reflected will decide the image position. So this is the image for what?
Mirror.
Image for which part? Lens or mirror?
Mirror.
And which image is this? Real or virtual?
Real.
Very good. Now the journey will not stop here. It will extend further. Just color. Now the red one, the light which you can see, is again the incident light for the lens, isn't it? So this point will also act as the object for lens. And which kind of object? Real. You can trace back, you can get the intersection. And then after the refraction, let's say they meet somewhere. I mean, I'll meet it nearby. You don't have space. So this is again called the image due to lens and the two real. So you can see the whole gamut of object and image. We never talked about the physical object. So of course we need some source of light, but the perception of image depends on the light, not on the reality. And that is why we say that what we perceive is the object. Okay. Sorry, what we see is the light ray, but what we perceive is the object. You don't see object, you see light. So your whole idea about the light, you translate into the object. For example, whatever you are seeing, that is your simply perception that you are seeing the object. But what you are seeing is the image formed by the light. So human beings don't see object. What we see? What we see?
Light.
We only see light. So what light enters the human eye will create the entire perception about the real world. So we say that we see light, but we perceive object. Okay, so we see light, but we perceive object. So our sense of object is basically only perception.
So,
So yes,
uh, so is it possible that object is real even if the incident ray, if we extend the incident ray and it meets forward?
pardon. 1 second.
So is it possible that object is real even though the incident ray is meeting forward?
If the object is real, then it is not possible, because if something is real, then light ray will only emerge. Okay. So if the light ray is kind of converging, it means it has suffered already some refraction. Okay.
Yes.
So if you can receive something like this, then no physical source can give you the converging incident light. A real source only creates a diverging ray. Okay, that's common sense. You understand? So anything which is real, I mean physical, not real, I would say, but anything which is physical will only emanate the rays or the light. So it will be diverging in nature. So object which are physical in nature can only diverge light. Okay. So converging light is not possible from a physical source. You can think about it. So if something is converging, it means it has come from the physical source and has already suffered some sort of reflection or refraction. Do you realize this? What I'm saying?
Yes. Understood.
So incident light, if it is converging, incident, it means it has not come from the physical source. That's simple. Okay. Because this chapter is all about ray optics, so one should be aware about the various properties of ray. Okay. So the first thing that we need to learn about the ray is called the. So I think object and image is clear. So okay, I'll mention some key points. So key features of object and image. So defined by object is defined by what? Incident ray. Image is defined by reflected or refracted ray. Okay, so that is how we define it. So these are two basic concepts about the object and image. The object is defined by the incident ray and image is defined by the reflected or refracted ray. Okay, it is clear.
Yes.
Yes, sir.
Okay, so now we can start with the first property of light ray, which is called the reflection property. Am I audible?
Yes.
Yeah. So we can start with the basic definition. What is the basic definition? A reflection of light. Okay. So the reflection is not just the property of mirror, rather property, the mirror is a concept which is like any surface which can reflect light can behave as a mirror. So what we call mirror? Any surface which can,
Reflect.
which can, yeah, which can, I mean, of course, the reflection is the phenomena of bouncing back of light from an interface to the same medium. So basically, in terms of energy, what we can say that either you transfer or throw back the partial energy or the full energy, both are a reflection. And the amount of energy which you throw back determines the intensity of image that you can obtain. So that's why when you look yourself in a pool of water, you can see your image, you can see yourself, but that image is not so bright because the water is being transparent, is able to refract maximum part of energy, and only a very small part of energy is thrown back, which is sufficient to form the image, but you don't see as a bright image. Understood?
Yes.
So the mirror is a concept. In fact, mirror is a concept, which means any interface which can throw back the light. So nowadays, because of the summer, if you go for the long drive, you can see the mirage, right? And these mirages are nothing but the reflection of light. Understood?
Yes.
So on roads,
Yeah, on roads. So that is called the atmospheric refraction, which leads to the reflection eventually. So light is able to bend I mean, the atmosphere, or you can say the air molecules of the atmosphere. Because of the temperature gradient bends the light in different fashion, and eventually the light suffers reflection. So it is like the light ray will come like this, will bend, and then will come back. So of course, it is not directly coming and reflecting. It is coming in bits and pieces, turning slowly and slowly, because the atmosphere will act as a layer of molecules, and because of temperature gradient, the density will vary from bottom to top. So during the extreme summer, the road is very hot, and because of this hotness, the air molecule will try to rise up. So we have the rarefied medium here, but as we go up, then density will increase, and because of the variation of density, we create something called the variable refractive index in medium, which creates this phenomenon. And we will come to that later on. So let's define it quickly. What is mirror? For mirror, we need not to polish by the silvering. The silvering is not the criteria of mirror. Mirror is simply a concept. Every lens is a mirror. Every glass slab is a mirror. Every prism is a mirror. In fact, every transparent object is also a weak mirror, because they are able to transmit maximum energy, but they're also able to reflect back some part of energy. The only thing which is perfect is called the total internal reflection, in which 0% get transmitted. And that's how we design the optical fiber cable for the transmission of data. Because data is essentially the form of energy, which is called, you can say, electromagnetic energy. And the loss of energy is quite possibly may lead to the loss of data also. So that's called the data integrity. So the data will or may lose some of its property. So to keep it intact, we use the optical fiber cable, which is capable of transmitting the data to a large distance in a very short time, because the speed of light is very high. It's 3 lakhs kilometer per hour per second. Sorry. So 3 lakhs kilometer per second is good enough to reach any part of the world in almost no time. Okay. So that's how we transmit the information across the world in almost real time. So it seems like everything is happening on a real basis, because the human reflex is up to few, you can say, millisecond or more than that. So if something occurs in less than 1/10 of a second, we are not able to understand. So if something happens in the 0.1 second and below, the brain will assume it as real. Whereas 0.1 second is sufficient for the light to travel across the world. So that is how the entire data is transmitting across the universe, I mean, across the world actually, at such a tremendous speed that it takes almost no time. But when we talk about the interaction with the planet, with the satellite which has lost the connection with the Earth, has gone to the exterior of the solar system, it takes time. So it may take maybe a few days for signal to reach, maybe few years to reach, because a satellite which has gone away from the Earth for the last 3-4 years will take some time to reach back. So when you talk about the interacting with stars are light years away, which means if I say 1 light year away means the light will take 1 year to reach here. So when you look at the star, the light which they released few billion years back is now coming to Earth. So whatever you see in the sky is the past, is not the present. So all the stars which you are visualizing now may not be actually present. They might have gone actually. And those stars which are born now, you will see again billions of years dead. Because we see light, so that's how you look at the past. You don't look at the present. So depending on the distance of object, our reality is kind of approximation. And thanks to the tremendous speed of light, which is still finite, there are certain phenomena which we can see distinctly, and there are some phenomena which we see concurrently. So the whole idea of phenomena depends on the speed of light, and that's why the world of computing or information sharing across the, you can say, globe follows the Einstein theory of relativity. So most of the systems which you hear today are designed by the world-best physicists and computer scientists, taking together the project and realizing the dream of the data transfer, okay, which enables the eventually the internet. So now today, if the internet is booming so much because of the Einstein theory of relativity. Okay, of course, difficult to understand as of now, but that's the real. So any surface which can throw back either partial or full, throw back incident energy are called mirror. In fact, your dish antenna. So you might have seen the dish antenna. It's like a round shape with slightly dent, so it's slightly curved like this.
Yes.
And
Yes.
in the disc antenna, you might have seen something, an object attached to this antenna at some distance, right,
Yes.
with the handle. So basically, these are called the parabolic reflectors. And the property of parabolic reflector is that if the light ray comes, if the any signal, which is the electromagnetic wave, comes from infinity or very far away place, we treat as a parallel beam of light coming here. Now these are invisible electromagnetic signal which you don't see, and these are reflectors. What the job of reflector is? To reflect back the energy back to the focus. So this is the parabola. This is the focus of parabola. I hope you have learned about the parabola.
Yes.
So the
Yeah.
device is located exactly at the foci. Understood? So when you locate at foci, then all the signal will be received after reflection. So this is also the case of reflection. But of course, the reflection is not of the light ray, rather the electromagnetic wave. And metallic surfaces, or you can simply say the metals, are really a very good reflector of EM wave. Understood? So mirror can reflect only the light ray, the visible spectrum, whereas the metals are good with the reflection of most of the electromagnetic radiation, because a thick metal will not let the light ray to penetrate much. So they prevent the transmission. Okay. And therefore, most of the energy is thrown back. So of course, you might have, I mean, experienced that during the rainy season, the signal gets disturbed, especially during the thunderstorm, because the thunderstorm creates a strong electric field in the sky, and these electric field interfere with the electric field which you are transmitting through the space, and these interference leads to the distortion of the signal or the loss of the signal. So your device is tuned to receive one particular frequency out of infinite frequency reaching the same reflector. So every channel, whether it's a Sony TV or GTV or whatever, so they are transmitting their own information. We can say the broadcasting the shows. So what they do is every show is a collection of sound and image. So basically these things are received separately. So they receive the sound, they receive the image, and they make a bundle of these two information. So eventually image will become the 0 and 1. Sound is also converted into 0 and 1. They make a bundle of these two information. The bundle is transmitted in form of EM wave by doing some modulation. And when the EM wave reaches back to the destination, by tuning your device to one particular frequency, resonance will occur, because you have might have studied in the SHM chapter. There is something called resonance, when the applied frequency matches with the original frequency.
Original.
So when
Yes.
yeah, so when you tune your device, when you tune your device to a particular frequency, then out of infinite channel in the space, you only receive the channel which creates the resonance, and that's how we filter the desirable channel out of so many channels available. Of course, this advancement has not occurred in one day. It has taken a decade of effort, not decade, I'm saying the millennium of effort, to make communication so much realizable that we don't even realize that what we are getting is something extraordinary technological advancement. Okay. So of course you pay for it, but that's simple. So you watch Netflix, and Netflix is the world's maximum consumer of energy, because everyone watching the Netflix will request the Netflix to release the movie onto the OTT platform. So the Netflix will transmit that movie from the server in the EM waveform, which requires tremendous energy. In fact, the world net electricity development, the 1% is consumed by Netflix. The rest of the world only consumes 99%. Imagine 1% is a huge number on a scale of Earth. So 1% of the total energy produced on Earth is consumed by only Netflix. Imagine that's if the world is earning 100 rupees, then 1 rupee is taken by you. So you are the 100th richest person in the world. Not 100, maybe the most, because you have almost 1% of the entire resource of the earth, which makes you the richest person actually. Yeah. Anyway, so coming back to the concept of reflection. Reflection is the idea in which you reflect back the energy. Reflection has nothing to do with the mirrors. Of course, mirrors are required for maximum transmission. So you want to transmit as much as possible. You use the silvering concept. You use polished mirror, and because they transmit more energy back to you, the reconstruction of image depends on the energy received. I mean, the reconstruction doesn't require much energy for the image formation, but the brightness of the image demand more energy. So by polishing the mirror, we make sure that we are able to reflect back maximum amount of energy. And when the image is reconstructed by the light ray, then the intensity received is really good, or you can say good enough. Okay,
Yes.
understood.
Yes, sir. Understood.
Okay, so what I was saying, I forgot this. Yeah, reconstruction. So there is something called intensity of image. So intensity is the mathematical term. Okay, and the brightness is the physiological term, like the way you feel it. So when I say brightness, it's a human thing, you can say. It's a brain way of perceiving intensity. When I say the word intensity, I mean the definition, the mathematical definition of intensity. So in physics, intensity is very much common, and the brain is something which can, I mean, tells you about the intensity, which is defined as the amount of energy which you receive per unit area and per unit time. That's called the intensity. So intensity is defined as amount of energy received per unit area per unit time. I have talked about this in the chapter of sound and wave. I hope so, if you remember. And the same is also true for any other energy
Yes,
form. So
sir.
not need not to be just a sound energy. It can be any electromagnetic energy. And for human brain, the brighter image actually means you are receiving more energy per unit area of your retina per unit time. So to reconstruct the image, the larger amount of energy is required. You see, even in the dark, you can see something. It is not like in dark we don't see at all. So in dark, what happens? The dark means you receive less photons actually. So there's nothing like a perfectly dark place. If we have a perfect dark, then it is a very disturbing. So you cannot keep on watching the perfect black for some long time. It will hurt your eyes. So not receiving light ray is something very dangerous. So anyway, the darkness is only called the gray dark. It's not the perfect dark. So in our life, we have so much photon spread that we don't get the perfect dark. Perfect darkness, no photon should be traveling there. No, that's not possible. So anyway, the intensity is the mathematical definition, and the physiological definition in terms of light is called brightness. And of course, brightness is proportional to the energy received. So a plane mirror with a polished surface will only make sure the reflection to occur more. Now, the expensive mirrors which you can buy, I mean, which are of course made by polishing the metal surface. Okay, so when we have the metal surface, what you see is the more accurate image construction because the energy is reflected back. So in older days, let's say a king or the queen, I mean, they used to create their own mirror with the actual silver. So they used to create the mirror with only silver metal because silver metal is a very good reflector and you can see your face uh, much better. Anyway, so coming to the mirror, we should know this. So quite an interesting fact about mirror we should know. And we can talk about the reflection. What is reflection? So phenomena of bouncing back of light upon hitting any interface, not surface, interface. So bouncing back of incident energy upon being incident on any interface into the same medium. So when any interface throws back the energy, so when any interface throws back the energy back to the same medium, then what we call
Reflection.
reflection. Reflection is a definition. Okay. Reflection is simply a definition. I hope that's clear.
Yes, sir.
Okay. Now we'll go to the very simple concept
So,
of, yeah.
so can you tell the difference between surface and interface?
Every surface is interface. Interface is defined for the medium. So surface, let's say if we have no medium, let's say vacuum, and then we have a, then we call surface. And when I say interface, then there are two medium. One ends and other begins, but we cannot differentiate where one ends exactly and the other begins. This is called interface.
Yes.
So interface is always to separate the two medium, and surface is only meant for one medium. Okay. So when I say surface of water, then I only mean the water, not the air. So when I say interface, then it is neither water nor air. It is something in between which we can't define. Understood?
Yes.
But if we have other side vacuum, nothing is there, like no material is present, then the interface becomes the surface. Understood?
Yes.
So laws of reflection. It's a very simple law, which you know. So the concept of law of reflection is a consequence of Fermat's principle of least time. Or you can say that if a light has to go from one place to other place, I might have explained in chapter of calculus. So if we have a light ray, let's say if you want to go from A to B, and you have some sort of a reflecting surface. Let's say we have A and B, as 2 point, and light wants to go from A to B. So there are two possibilities. It can go directly. So it will, if it goes directly, then it will take the least time for sure. But we are interested in going through reflection. So there are many possibilities of going from A to B. So there are just infinite paths possible. So now out of this infinite path, how the light ray will choose the correct path?
Sir, please will you
So
repeat?
the light ray will choose the path. See, out of A, see, to go from A to B through reflection, we have infinite path actually. So out of infinite path, which path the light ray will choose? That's the question. And the answer is the light ray will choose which path?
So the path in which the angle of reflection is equal to angle of incidence with respect to normal.
No, no, that's not the answer. That is the consequence actually. The path it will choose is the path which offers the least time to go. Okay. So light light follows the principle of least time. It always go in the least possible time. So it will choose the path which will have the least time, and that's how becomes the this that process becomes the law of reflection. So this is called the Fermates principle, and that is a core property of light. So using that property, every other property can be derived. The least time Fermat. Okay. So for example, if we have a plane mirror, let's say this is a plane mirror, and let's call there are 2 points A and B. So let's drop a perpendicular first of all. So I have no idea how the law should be, but to start with, I assume some random location, and because I have no idea, as I said, I can just do a normal like this, and I will prove it mathematically that the alpha and beta must be equal. Right now, I don't know the alpha. So what do I do is the point P can be anywhere between these two extreme points. If I call this as x, this will be, let's say, d minus x. Let's say d is the separation. Okay. So d is the separation, and alpha and beta are the angles. Let's call the height as h1, this height as h2. We don't know that. We are just checking the random points. So light ray will travel from A to P and P to B. So the total time taken for the light to go from A to B after reflection is how much? AP plus PB upon Let's say the speed of light is c, or you can say v, depending on the medium. Because it's the same medium, so we can call it v. If it is air, we can call it c. If it is vacuum, we can call it c. So let's take any wavelength. So t we can write as how much? 1 by c into what is ap?
H1 square plus x square
And what is bb?
d minus x square plus h2 square.
So you can clearly see that t is a function of x. So for t minimum, the first derivative must be 0 first of all. So if you multiply c is constant, so c into t, so dt by dx 0, then 0 equals to, and I hope you know the differentiation of the function. It will give you
Yes.
x upon x square minus x h1 square plus x square, and this will give you how much? Minus, okay,
Minus x square.
d minus x upon the entire term. I have taken the chain rule and all and differentiated, and I have cancelled the 2 actually, and minus will come. So if you equate to 0, you can see clearly that x upon the hypotenuse, so I can add like this, x upon ap equals to d minus x upon pb. And because this is alpha, this is also alpha, and this is beta, this is also beta. What is sin alpha? X by ap. What is sin beta? D minus x by bp. So if the sin alpha is equals to sin beta, then alpha equals to beta. Understood? So in
Yes.
the reflection property of light, the minimization, the optimization concept is inherent actually. So light follows the principle of least time. So to go from one place to other place, it will choose the point of hitting which can take you there with the least time, and that's how only those light ray hitting the point P will be reaching the B. All other light ray hitting other point will go somewhere else, will not go B for sure. So the P must be selected such that alpha equals to beta. Understood? It's clear.
Yes, sir.
So that's the law of reflection. Rest you know from class 10th that incident ray, normal, reflected ray lies in the same plane, and A equals to alpha equals to beta, I equals to R. So these things I'm not going to write. You can go and reach the class 10th optics. So the whole idea of geometrical optics is to understand the time relation of light, and to solve most of the challenging problem. I'm of course not the typical SC1 problem. You need to understand the time relation, the time minimization, the optimization, or to choose the optimal path. So in fact, the concept of refraction is not different. The refraction is also having the same, exactly same phenomena. So let's say if you have a friend, if you live here and if you want to go to meet your friend at a point B, then definitely joining the A and B looks like the smallest distance, which is not the case. Why? The smallest distance cannot be the smallest time. Light has to do with the time, not with the distance. So maybe if we have a two paths, two route to reach the destination, one with the freeways and highways, and other with a single lane road. The single lane road may be 10 kilometers and the highway may be 20 kilometers, but you can drive really fast on the highway. So maybe you can drive at 100 kilometers per hour, but in the lane you can only drive 20 kilometers per hour. So it will take 5 times more time. So we choose the path which offers the least time, not the least distance. Okay. So to go from A to B, there are many possibilities, and the one possibility is you can go here and come back. But I think this is really foolish because you're unnecessarily increasing the time by more than this value. So that's a foolish option. So what I can do is I can drop a perpendicular from here. So one thing is clear that light ray has to hit something between the points, let's say P and Q, to go to B point. Okay. Now to go from A to B in the least time, we should know that the light can travel faster in the rare medium and it travels slowly in the denser medium, right?
Yes.
So if I say this velocity is V and here the velocity is C is more than V. So this is vacuum. Okay, it looks like vacuum. And this is the medium. So definitely you want to minimize this time. You want to cut short the length in the medium. So you want to travel less in the denser medium. So to travel less, you can go somewhere here. You can hit the, and if you hit something here, the length which you travel in the denser will reduce. You can see it. And by this proper selection, you will realize that the minimum path will be the path which follows the exactly Snell's, the law of. Understood.
Yes.
And you can see clearly the light ray is bending towards the normal. If you think that way, the Snell's law. But light is bending towards the normal is not the answer. The answer is the light is following the path with least time. Understood.
Yes.
And you can again prove by the same method. Let's call H1, let's call H2, let's call alpha, let's call beta, and so on. Or you can say I and R. So the time taken to go from A to B will be how much? Let's call it O. So time will be AO upon the speed of light in the first medium. Let's call it V1. I mean, just to make it a general formula. Let's call it V. Plus, you will travel O to B with a different speed V2. And therefore, you can clearly see that AO is how much? H1 is okay. Again, you can do the same thing, X and D minus X. Plus X squared by V1. I'm proving all the formula here at once. And then for T minimum, the dt by dx should be equal to 0. And if you differentiate to 0, what you get is, so you get, I can directly add the sine alpha, because if you remember earlier we got sine alpha, the first term after differentiation.
Yes.
But V1 will be also there because you cannot take V1 common and cancel. You get sine alpha upon V1 and sine beta upon V2 equals to 0. Is this clear?
Yes, sir.
Or you can differentiate more rigorously, rigorously, and you can get the answer. So you can see alpha is here. This is also alpha. That's why we got this answer. This is beta. And therefore, the sine alpha upon V1 is sine beta upon V2. And if you multiply with the velocity of light both sides, then later on we come to know, or you might have studied that the C by V1 is called refractive index. So you can say N1 sine alpha and you can also write this N1 sine, or you can say angle of incidence equals to N2 sine angle of refraction. So what you need to realize that Snell's law is a consequence of time minimization. So by applying the Snell's law, you default by default you choose the a path which offers the least time. These are the time phenomena basically, and light exhibits such a phenomena naturally. So the nature is following the optimal path condition. So optimal path means optimal time condition. Okay, so only those paths light ray will choose which can offer the least time to reach at the destination. These things we can also prove using the the concept of Snell's law, the concept of wavefront, and other concepts. So in the chapter of wave, you will come to know the alternative proof of the same. That's very interesting, and you will learn about the proof. I can give here also, but the concept of wavefront is not known to you, so it will be difficult. Let me just show you how it looks like. One, two, one. So the red line is like a plane. You can think as a plane into the this blackboard. So it's a plane. Yeah, these are called the wave fronts. If you enter a denser medium, then it will travel with lesser speed. Okay. So the Huygens principle. So this wavefront will now look at the point P. The P will reach the P dash in how much time? So let's say if the speed is V1, so the time in T it will reach, let's say, by traveling V1T. So the P will go to P dash by traveling V1T in time T. But in the other side of the medium, we have I mean different speed. Let's say V2 is more than V1. So this point act as a source of wave, and it creates a wavefront. But this wavefront will travel very small distance. Why? Because the speed has decreased, so it not travel more. So this we call the wavefront of the other side of the light. So by the time the P reaches P dash, the wavefront will change the shape. You can see. I will just do like this. And what I'll do is I'll just make it smaller. And the property of the light ray is that it always travels at right angle to the wavefront. So this will travel V2T, and this is at right angle. So what is interesting here? So if I draw a normal, and if I draw a perpendicular to the wavefront, so this is right angle. This is called angle of incidence because this is the light ray, and this alpha, this is also alpha. And similarly, if you do the same thing, This is the beta. This is also beta. And using the simple triangle, the trigonometry, you can add sin alpha equals to the perpendicular upon hypotenuse, which is v1t upon let's call it o dash. No, this is p dash. This is s dash. Yeah. So v1t upon sp dash. Sp dash is the common side of the two triangles, and sin beta you can say as v2t by sp dash, and therefore sin alpha upon sin beta. So sin alpha upon v1 is same as sin alpha upon beta. So again, this is the Snell's law which you can convert into. If you have not understood this part, don't worry, because you need to learn the Huygens principle. Just a minute. Okay. So there are many ways in which the Snell's law or the law of reflection can improve. Okay, the whole idea is the time minimization, and this idea will be really helping you in getting some of the challenging problems. So if a light ray has to reach a point by following two different paths, it will choose the path which offers the least time. Or you can say for the image formation, let's say if the two light ray wants to form the image. Now to form the image of an object by two rays, they must intersect. You can see that. Let's say these two are intersecting. Now if I create the source here and here, imagine. So the light ray which will leave now, will they meet here or someone else will meet? Who will meet?
So can you repeat the question?
Let's say we have two sources of light. One is here, other is here. So imagine the light is like a small dot or some kind of pulse. If both pulses will leave at the same time, will they reach here in the same time? Because I think if the first pulse will reach here, the second will be somewhere here only, na? Because they have different distance to travel, isn't it?
Yes, yes.
So to reach at the same place, they must leave at different time.
Yes.
So in case of light, to form the image, the rule is the light must leave at the same time and must meet at the same time. Only those who leave at the same time and meet at the same time will reach the destination. Understood? I'll just show you something interesting. I mean, how the time concept is so powerful. Why we should think in terms of time.
So then line should be symmetrically.
Yeah, it should be symmetrical, right? But look at this scenario. And we are talking about the two light rays which are very close, not very far. So generally, we talk about the closer rays to do the image formation. So let's say we have a surface which may be a parabolic in nature, maybe. Let me draw something interesting. So imagine there are two light rays, one coming along this line, another slightly going up. So we can just for the sake of it's like here, almost here. But I'm just showing it slightly moving. And let's say if I draw a perpendicular, and then this light ray travels and reaches somewhere. Let's say it forms the image at this point P. Now the rule is if I call this as uh, the gap as x, the height is h, then the time that the light ray will take. So because here, if I want to compare the two paths, before this line, everything is same for both the paths. So they have traveled so far same value. And then the first light ray will travel in the vacuum and then medium. And the second will travel from here onwards to the medium. So what I can say, if I call this as let's call this as, so from the interface, if I call the F full as D, this will become D minus X. So I'm taking D from the interface till the point P. So this becomes how much? Under root of H square plus. So to compare the time, I will start from here, this point, for the upper ray, and for below ray, it will start from the A dash. So to go from A to B, let's call it, this is A, this is B. So the time taken by the first ray to reach the point P will be AB upon vacuum plus BP upon speed of light you will come to know, or in fact you must know, is C by mu. If you enter the medium, it decreases, right? And the T2, the light ray will travel the entire distance D by mu. I mean, sorry, D by C by mu. And to form the image, the light ray must reach at the same time. So by equating T1 equals to T2, then only the image will be formed. What you can write is that AB upon C plus mu dp upon C equals to mu d upon C. C cancels out. So we have a nice relation AB plus mu BP equals to mu. And then AB, how much is it? X plus mu under root of. So you can write as mu squaring both sides. So let's expand this. Okay. So you may get some relation between the y and x. I mean, they may give you the y and x, something will be given to you. So what the idea is like, if the light rays should travel and reach at a point, the time taken should be equal. So we always think in terms of time to solve the questions like this, which is not following the regular spherical mirror formula and the spherical lens formula. So in your syllabus, the formula which you will be deriving are only meant for the spherical surface. The moment you receive the random surface with a different set of equation, the way to solve is the time equality. So you will always try to find the time to go from the place to the point, and by equating the time, we solve the general optics problem. Understood?
Yes, sir.
Yeah. So we can do that way. So anyway, this was just like one idea that why and when the time concept is required to solve the numerical. Understood?
Yes, sir.
So see, I mean, for typical knowledge, I will be sharing the notes which you can read and understand. So what I will be teaching is the only numerical which is slightly difficult and advanced. Okay. So what I will believe that you guys will read on your own, and in lecture I will discuss most of the difficult theory and difficult problems. Understood? So I'm going to share a notes very soon, maybe in 5 minutes. Go through it today only, at least the mirror chapter. Okay, and we'll
Sir,
see
up
the
to?
up to only plain mirror, only plain mirror. So we will studying the I mean steps. We will first read the plane mirror, then we read the spherical mirror, then we start the refraction, then we have reflection from slab, then reflection from prism, then reflection from the lenses, then combination of lenses, then the various type of instrument, telescope, microscope, compound microscope, then various types of defects of vision, myopia, hypermetropia, astigmatism, and once we finish all of this, then we'll finish the ray optics. There are I mean, the variety of things that I will discuss as a theory. If I feel that okay, I need to teach for the first time, I'll teach. If I think that I can read and read the notes and understand on your own, you can do that as well. But you have to almost be regular with reading the notes, because definitely I'm not going to cover every small aspect. That is high school things, and I hope that you know how to do the red diagrams. Okay,
Yes,
so I
sir.
will also give you some some effective red diagram concept, and what I will expect that you will be also, I mean, knowing the basic red diagrams which you have studied in class 10. So do revise red diagrams and then come back. Okay. Okay. I'm going to share right away.